Alrighty, welcome back in, everybody. I hope you're having a wonderful day so far. My name is Michael, and welcome back to the channel. We're going to be jumping back into MIT OpenCourseWare 6.0002 from fall 2016, the Introduction to Computational Thinking and Data Science course. We are on Lecture 5, Random Walks, with John Butag today. We're going to be discussing how to build simulations and plot graphs in Python. So this is going to be a great lecture, and if you guys have missed the previous lectures or are wanting to follow along, I'm uploading these as a series to my channel as a re-upload watch-along series, as well as you can catch this live right now. Hello to those that are here live and watching this. I stream every single day around 7 p.m. PST after my 9 to 5 job as a chemist. So we are going to continue on here with the course, teaching ourselves computer science every single day. Cool. Let's get into this.
All right. Today we're starting a new topic, but it is, of course, related to previous topics. As usual, if you go to either the 60002 or the 600 website, you'll find both today's PowerPoint and today's Python. You'll discover if you look at the Python file that there's quite a lot of code in there. And I'll be talking only about some of it, but it's probably all worth looking at, and a fair amount of reading associated with this week. All right, why are we looking at random walks?
Hey, Austin, how's it going, my guy?
Picture here of, think of them as molecules just bouncing around. This is actually a picture of what's called Brownian motion, though Robert Brown probably did not discover it.
Okay, why random walks?
We're looking at random walks because, well, first of all, they're important. In many domains, there are people who will argue, for example, that the movement of prices in the stock market is best modeled as a random walk. There's a very popular book called The Random Walk Down Wall Street that made this argument. And a lot of modern portfolio analysis is based upon that. Those of you who are not interested in making money, and I presume that's most of you, it's also very important in many physical processes. We use random walks, say, to model diffusion, heat diffusion, or the diffusion of molecules in suspension, et cetera. So they're very important in a lot of scientific and indeed social disciplines.
Nice.
They're not the only important thing, so why are we looking at those? Because I think it provides a really good illustration of how we can use simulation to understand the world around us. And it does give me an excuse to cover some important topics related to programming. You'll remember that one of the subtexts of the course is, while I'm covering a lot of what you might think of as abstract material, we're using it as an excuse to teach more about programming and software engineering, a little practice with classes and subclassing, and we're going to also look at producing plots.
Okay.
All right.
Drunkard's walk.
So the first random walk I want to look at is actually not a diffusion process of the stock market, but an actual walk. So imagine that you've got a field which has somehow inexplicably been mown to look like a piece of graph paper, and you've got a drunk sort of wandering around the field, taking the step every once in a while in some random direction. We can then ask the question, is there an interesting relationship between the number of steps the drunk takes and how far the drunk is from the origin at the end of those steps? You could imagine that if the drunk takes more steps, he's ever further from the origin. Or maybe you could imagine, since it's random, that he just wanders away and he wanders back in all directions and more or less never gets very far.
Yeah.
So just out of curiosity, I'll take a poll. Who thinks that the drunk doesn't much matter how many steps he takes, he'll be more or less the same distance away? And who thinks the more steps he takes, the further away he's likely to be?
Yeah, I think it's just going to kind of, he'll be closer to where he started.
When you take polls, they come out almost tied.
I don't think he'll get very far.
All right. So let's look at a small example. Suppose he takes one step only. Well, if he takes one step, he could And we'll assume for simplicity that he's not so drunk that he moves at random. He either moves north or south, east or west.
They changed the pictures.
These are all the places he can get to in one step. What they have in common is that after one step, the drunk is always exactly 1 unit away from the origin. Well, how about after 2 steps?
It could be 2,
So
or it could be
without loss
back
of
at the origin.
generality, let's assume that the first step,
Or 1 step away.
let me use the pen that you're supposed to use to write on this, rather than this pen, which would make a real mess on my screen. Without loss of generality, we'll assume that the drunk is there after 1 step. Took 1 step to the east. Well, after 2 steps, those are all the possible places he could be. So on average, how far is the drunk from the origin? Well,
About
if we
1
look,
step.
he could either be 2 steps away if he took another step east, 0 steps away if he took a step west, or what do we see for the top 2? Well, the top and the bottom one, we can go back and use the Pythagorean theorem. C squared equals a squared plus b squared.
Yeah.
And that will tell us that it'll be the square root of a squared plus b squared. And that will tell us how far away the upper 2 are. And then we can just average them and get a distance. And as we can see, on average, the drunk will be a little bit further away after 2 steps than after 1 step. Well, how about after 100,000 steps? It would be a little bit tedious to go through the case analysis I just did, right? Mm-hmm. There are a lot of cases after 100,000 steps. So we end up resorting to a simulation.
Nicely.
So we'll
Python
structure
is
it
my
exactly
first
the same way we've been
kind of main
structuring our other
language, yeah.
simulations. We're going to simulate 1 walk of k steps, n such walks, and then report the average distance from the origin of the n walks. Before we do that, in line with the
So 1
software
walk of
engineering
k steps,
theme
you're going
of
to
the
do a bunch of
course,
different walks and
we'll
report the
start
average.
by defining
Gotcha.
some useful abstractions. The 3 of them I want to look at: location, the field that the drunk is in, and the drunk, him or herself. All right, so let's first look at location. This is going to be an immutable type.
Yeah.
So what we see here, as long as I can't point on the screen, I'll point with a pointer, is that
You have
we'll
x and y are
initiate it,
floats.
we'll
So
initialize
there's
it
just
to
the location
an
x and y values.
That makes sense. We'll be able to have 2 getters, get x and get y. And here's how we see it's immutable.
Then you return
What
a new
move
location
is doing
on a
is it's
move.
not changing the location, it's returning a new location.
A new location, yep.
Perhaps move is poor choice of name for that, but that is what it's doing. It's just returning a new location where it adds the change in x and the change in y to get 2 new xy values. Notice, by the way, that I'm not restricting these to be integers or 1 or anything like that. So this would work even if I did not want to take those nice little east-west, north-south steps. I've got a underbar string, str, and then here's my implementation. You can see it's very sophisticated, of the Pythagorean theorem. So I just do it that way, and that will give me the distance between 2 things. It's one of the annoying things about classes, and actually all languages I know with classes, is you would like to think that self and other, there's a symmetry here. The distance from self to other is the same as from other to self, but syntactically, because of the way the language is structured, we treat them a little bit differently. All right. How about class drunk? Well, this is kind of boring.
Just
Drunk
a
is a
name.
name and
If
a
no
string.
name, return anonymous.
And that's all. Well, the point of this, and I don't think we've looked at this before, is this is not intended to be a useful class on its own. It's what
Abstract
we
base
call a
class.
base class. The notion here is its only purpose is to be inherited. Okay, it's not supposed to be useful on itself, but it does give me something that will be used for the two superclass or subclasses. And we'll look at two subclasses, the so-called usual drunk,
Usual
the one
drunk.
I tried to simulate when I was wandering around, who wanders around at random, and a drunk I like to think of as a New Englander or a masochistic drunk who tries forever to move ever northward because he or she wants to be frozen. I do like this picture of entering the state of Maine in the winter.
Shout out Maine, shout out all the frozen.
So here's the usual drunk, subclass of drunk, and it can take steps at random, one step, either increasing y,
Take step, it
north,
can increase.
decreasing y, a
You
step
turn a random
south,
random step.
increasing x, a step east, or decreasing x, a step west. So those are the choices, and it's going to return one of those at random. I think we saw random.choice
This one goes
in the last
upward.
lecture.
This one goes down.
And then our masochistic
left,
drunk, it's
right, and
almost the
left.
same, except the choices are slightly different. If he chooses to head north, he doesn't go one step, he goes 1.1 steps north.
You go
If
south.
he chooses to go south, he only goes 9/10 of a step. So what we're seeing here is what's called a biased random walk. And the bias here is the direction of the walk
northward bound, yeah.
that is moving either up or down.
You have a absolute
Okay.
sum of positive, right?
Pretty simple.
In the north direction for this step.
How about just to test things out, we'll ask the question, is this an immutable or a mutable type? Are drunks mutable or immutable? This is sort of a deep philosophical question.
Well,
right?
you can mute
But
a
if we
chunk
ignore the
of,
philosophical underpinnings of that question,
probably not.
what about the two types here? Who thinks it's immutable?
I'm gonna say it
Who
is
thinks it's mutable?
immutable.
All right. Why do you think it's mutable? What's getting changed? The answer is nothing, right?
Clutch. Yes.
It gets
It's
created,
immutable. Phew.
and then it's returning
Just a random
the
choice
step,
of preset
but it's
values.
not actually changing the drunk. So far we have two things that are immutable, drunks and
Yes.
locations.
Look at us. Let's go.
Let's look at fields. Fields are a little bit more complicated.
Okay.
So
we have a
field
drunk
will be
dictionary. So we're going to add a drunk to the
and the
dictionary with a drunk
dictionary
and
is
its
going to map
location.
a drunk to his or her location in the
And then the
field.
get location just gets the
So we
location
can
from
add
the key of the drunk.
a drunk
Okay.
at some location.
Easy. Very
And
easy.
we're going to check. And if the drunk is already there, we're not going to put the drunk in. We're going to raise a value error, duplicate drunks. Otherwise, we're going to
Duplicate.
set the value of drunk in this mapping to loc. And now you see, by the way, why I wanted drunks to be immutable. Because they have to be hashable so I can use them as a key in a dictionary. So
Yeah.
it's not an idle question whether they were immutable. It was an important question. I can get the location of a drunk. If the drunk is not in there, then I'll raise a different value error, drunk not in field. Otherwise, I'll return the location associated with that drunk.
Yeah. Now we have a move drunk, which takes the
And
drunk.
finally,
if drunk not in
We're
self
going
drunk,
to
so
have
you raise a value
move
error.
drunk.
You take step,
Again, I'll check
returning its
whether
x
the
and y
drunk is there.
distance of the drunk.
If the drunk is there,
And
I'm
then
going
you
to get
move
the
by those
distance
x and y
on
distance.
x and the distance in
So
y
you get the random step,
by
right?
calling drunk.takeStep.
Which is that method that takes
All
a
right,
step
so we saw
for
a take
depending
step
on which
for a
drunk.
drunk didn't move the drunk anywhere because the drunks were immutable, but returned
The
new
step it took
locations,
it, right.
so new x and new values, and then
I
I'm
think
going to use
It
that
changed updated values, like
to
delta
move
values.
the drunk in the field.
And then you add,
Okay?
you call move, which
So I
adds
said
those delta
self dot
values
drunk
onto
drunk
its
to
current
move
location.
x distance and y distance. All right? So it's very simple.
Yeah, here's
But
the
having
deltas.
built
Yeah,
these-
you take the deltas and apply
This
those
set of
to the x and the
classes,
y.
we can now actually write the simulation. Oh, what about classes? Are they mutable or immutable? Not classes. What about fields? Any votes for mutable?
You mutate the drunk
Yeah,
variables.
exactly.
Yeah.
Because you can see I'm mutating it right here. I'm
Yeah.
changing the value of the dictionary. And in fact, every time I add a drunk to the field, I'm changing the value of the dictionary, which is to say mutating the field.
Yeah.
So I'll have a bunch of locations which are immutable objects. Makes sense that a location is immutable. A bunch of drunks, and the thing I'm going to change is where the drunks are in the field.
Yep.
All right? I said we'd start by simulating a single walk. So here it is, a walk in a field.
Given a drunk with a number of steps.
With a drunk, and that drunk will take some number of steps in the field.
So you start at field get location of the drunk.
And
for
you can
every
see this,
step
it's
in the number
very
of
simple.
steps
I
you
just have a
move the
loop.
drunk.
Drunk takes some number of random steps.
You field dot
and
move
I'm
drunk.
going to return
and then you return the distance,
from the start.
Right. You just make
to
running a
the final
simulation
location of the
across
drunk.
a single drunk, right?
All right, so how far is the drunk from the origin? I then need to simulate multiple walks. Notice
Multiple
here
walks.
that I've got the number of steps, the number of trials, and
So number of steps, and
D
now the
class
number of
stands
trials.
for class of the drunk. And that's because I want to use the same function to simulate as many different kinds of drunks as I care about. We've only seen two here, the masochistic drunk and the usual drunk, but you can imagine many other kinds as well.
Yeah.
So let's do it. So here I'm going to simulate a walk for one drunk, Homer. So we'll create a drunk named Homer, or the variable
And its
Homer.
location is at 0,
is
0.
The drunk class.
For a number of trials, you create a
And the
field
origin.
and you add a drunk, and then you do
Distances.
distance append, and you
And
call
for
a
t and
round
range
of a
number
walk,
of trials,
right?
we'll
And then
just
one step.
do it, and then we'll return the distances. So it's initialized to the empty list. So we're going to return a list of, for however many trials we do, how far the drunk ended up from the
This
origin.
is the round. One's on the
Then
round.
we can
number of
average
trials
that, and we look
is
at the mean.
reused
Maybe we'll
here
look at the min or the max.
as the number of
Lots
walks
of
to do
different
per
questions
trial.
we could
too.
ask about the behavior.
Okay.
And now we can put it all together here. So drunk test will take the length, a set of different walk lengths, a list of different walk lengths, the number of trials and the class. And for number of steps in walk lengths, distances will be sim walks of number of steps, number of trials,
Okay,
D
so
class.
for number of steps in the walk lengths,
And then I'm going to just print some statistics.
right, we're going to sim walks.
You may or may not have seen this. This is something that's sort of built in to Python.
Gotcha.
I can ask for the name of a class.
Got it. Jeez.
So D class, you remember, is a class,
Come on,
and
Mike, wake up.
underbar name will give me the name of the class. Might be usual, it might be drunk in this case. Okay?
Okay.
So let's try it.
Let's try it.
All right, so the code we've looked at. So let's go down here and we'll run it, and we'll try it for walks of 10, 100, 1,000, and 10,000 steps, and we'll do 100 trials.
Why do I keep yawning? Oh my gosh. Come on. Wake up. Come on.
All right, here's what we got. So my question to you is, does this look plausible?
Does this look plausible? Right, so usual drunk walks 10 steps.
What is it telling us here? Well,
The
it's
maximum
telling us
drunk
here
got
that
here.
the length of the walk actually doesn't really affect, the number of steps doesn't affect how far the drunk
Means
gets.
pretty consistent.
Yeah, there's some randomness, 8.6, 8.57, 9.2, 8.7. Not much variance.
Yeah.
So we've done the simulation and we've learned something.
Man, I gotta stop yawning.
Maybe. So does this look plausible? We can look at it here.
Even for 1,000 steps, you
transcribed
never
it.
really gets too far.
What do you think? Well, go
Even
ahead.
at 10,000 steps, you know, it doesn't change.
After the first 2 steps, there's like a 50% chance of going closer to the origin.
Right.
50% chance of going away from it.
So we have at least one vote for plausible, and it's certainly a plausible argument.
Is this kind of like the leak code problem that we were discussing? You know, the medium one that we did not too long ago, where it is like the first person on a plane forgets their ticket. Like, what is the likelihood or odds that, you know, every other, you know, at the nth person or the ith person given will also, you know, sit in their seat or have to sit in a random seat, right? It's kind of, I think it's kind of like that.
Argument. Well, one of the things we need to learn to do is whenever we build a simulation, we need to do what I call a sanity check to see whether or not the simulation actually makes sense. So if we're going to do a sanity
really
check,
excited
what
about
might
this.
we do in this case?
He's really excited.
We should
Let's
try
try
it on cases where we
know
think
the
we
answer.
know the answer. Right? So we say, all right, let's take a really simple case where we're pretty sure we know what the answer is.
So
Let's run our simulation and make sure it gives us the right answer for this simple case. So if we think of a sanity check here, maybe we should look at these numbers. We just did it. We know how far the drunk should get in 0 steps. Right? How far should the drunk move in 0 steps? 0.
0.
How far should the drunk move in 1 steps? We know
1.
that should be 1. 2 steps, well, we knew what that should be. Well, if I run this sanity check, these are the numbers I get.
You shouldn't have been able to move
I
with
should
0
be
steps.
pretty suspicious. I should also be suspicious. They're kind of the same numbers I got for like 10,000 steps. What should I think about? I should think that maybe there's a bug in my code. So if we now go back and look at the code, yes,
Hey,
this
Purple
is Bill's
Vision.
the pants on fire test.
Yeah, pretty much we're following the MIT
There's
60002
clearly
course
something
right
wrong
now.
with
We're
these
on lecture
numbers.
5, random walks.
What we were appending is walk of Homer num trials 1. Well, num trials is a constant. It's always 100.
Yeah.
What I intended to write here was not num trials, but num steps. But it was, you know, I actually did this the first time I wrote this simulation many years ago. I made this typo, if you will, and I got these bizarre answers. So I looked at the code and I said, well, that's actually wrong. No wonder it's always the same number. I'm calling it with a
calling for
constant.
the same number of trials
The
every
constant
single
happens
time.
to be 100. So let's go fix the simulation.
So you're only walking on that same constant. Yeah. Zoom it in here.
So this should have been. Now let's run it again.
All right. 89,
Well,
27,
these
8,
results are
and
pretty different.
2.8. Yeah, so it gets dramatically
Now
bigger.
we see that, in fact, they're increasing. Should I just look at this and be happy? Probably not, right? I should run my sanity check again and make sure I get the right results for 0, 1, and 2. So let's go
Right.
back and do
You can
that.
see that now
just to
that he
be a little
changed
bit
that, you can see
safe.
kind of this increasing first step increase.
So I'll just change
And
this
same
tuple
with
of
the,
values to be.
The other type of drunk. Well, he actually comes downward on 1,000 steps.
And I should feel a lot better about this, right? All right, the mean, the max, and the min are all 0 when he doesn't take any steps. 1 is exactly what we should expect.
1 and 1.
And 2 is also, the mean is where we would guess it to be. And the max is 2, happened to take 2 steps in the same direction. And the min is 0, happened to end up where he started. So I've passed my sanity check. Doesn't mean my simulation is right, but at least I have reason to be hopeful. So,
yeah.
All right, getting back.
Okay. Let's visualize the trend now with some matplotlib here.
So we saw these results. And now we're getting the indication that, in fact, contrary to what we might have thought, it does appear to be that the more steps the drunk takes.
Hey,
further
Jow, how's it
away the
going?
drunk
Welcome
ends
back
up.
in, my guy. Welcome in.
And that was the usual drunk. We can try the masochistic drunk, and then we see something pretty interesting.
There's 1,000 steps here.
I won't make you sit through it, but when we run it, here are the usual drunks, the numbers, and I just looked at it for 1,000 and 10,000, so it would fit on the screen. You see for the usual drunk, it's 26.8, 90, roughly 90, fair dispersion in the min and the max. And the masochistic drunk seems to be making considerably more progress than the usual drunk. So what we see is this bias actually appears to be changing the distance.
Yeah, because this one has that northward bias, right?
Well, that's kind of interesting. Now we could ask the question, why? What's going on? And to do that, I want to go and start visualizing what's the trend. So rather than just looking at 2 numbers or n3 numbers as we've been doing, I'm going to draw a pretty picture.
Yeah.
Actually, I'm not going to draw. I'm a terrible artist, but Python will draw some pretty pictures. We're going to simulate walks of multiple lengths for each kind of drunk, and then plot the distance at the end of each length walk for each kind of drunk. All right, I now digress for a moment to talk about how we do plotting. So we're going to use something called PyLab. I've listed here
PyLab.
4 really important libraries that you will surely end up using extensively if you continue to use Python for research purposes. NumPy adds vectors, matrices, and many high-level mathematical functions. Actually, it might be NumPy, it might be NumPy, I'm not sure how to pronounce it, but we'll call it NumPy. So these are really useful things. SciPy adds on top of that a bunch of mathematical classes and functions useful to scientists. Things like, well, we'll look at some of them as we go on through the term. Matplotlib adds an object-oriented programming interface for plotting. Anybody here use MATLAB? Great. Well, you'll find that Matplotlib is the think MATLAB, lets you in Python use all the plotting stuff that you've come to either like or hate in MATLAB. So it's really convenient. If you know how to do plots in MATLAB, you'll know how to do it in Python. PyLab combines all of these to give you a MATLAB-like interface to Python. So once you have PyLab, you can do a lot of things that you would normally want to do in MATLAB. For example, produce weird-looking plots like this one. All right, I'm going to show you one of the many, many plotting commands. It is called plot. It takes 2 arguments, which must be sequences of the same length. The first argument is the x-coordinates. The second argument is the y-coordinates corresponding to the x ones. There are roughly 3 zillion optional arguments, and you'll see me use only a small subset of them.
All right, so we'll go.
It plots the points in order. First the first xy, then the second xy, then the third xy. Why is it important that I say it plots them in order? Because by default, as each point is plotted, it draws a line connecting one point to the next point to the next point. And so the
First
order in which they're
two.
plotted will determine where the lines go. Now, we'll see as we go on that we often don't draw the lines, but by default, they are drawn. Here's an example. You start by importing Pylab. Then I've given x vals and y vals 1. And if I call Pylab.plot of x vals, y vals 1, here is one of the arguments I can give it. I'm saying I'd like this to be plotted in blue, B for blue, and I'd like it to be plotted as a solid line, a single dash. And I want to give that line a label, which I've said is first. Y vals 2 is a different list. I'll plot it again. Here I'm going to say I want a red dotted line. And
We've used matplotlib before, so this is pretty
And then after plotting it,
simple.
I'm going to invoke pylab.legend, which puts this nice little box up here in
Getting
the corner.
these
in this
notes
case,
jotted down for you guys.
saying that first is a solid blue line and second a dotted red line, or a dashed red line, I should say. Now, again, there are lots of arguments, lots of other arguments I could have given plot. Also, legend, I can tell it where to put the legend if I so choose. Here I've just said put it wherever you happen to want to put it, or Pylab wants to put it. All right, so a very simple way to produce a plot. There are lots of details and many more examples about plotting in the assigned reading. We posted a video that Professor Grimson produced for an online course, 600.1x. It's about a 50-minute video broken into multiple segments about how to use plotting in Pylab with a lot more detail than I've given you. You'll see if you read the code for this lecture, and as you see this lecture, there'll be lots of other plots showing up of different kinds. These are my two favorite online sites for finding out what to do. And of course, you can Google all sorts of things. That's all I'm going to tell you about how to produce plots in class, but we're going to expect you to learn a lot about it, because I think it's a really useful skill. And at the very least, you should feel comfortable that any plot I show you, you now, obviously not right now, but you will eventually know how to produce. So if you do these things, you'll be more than up to speed. All right. Started by saying I wanted to plot the trends in distance. And they're kind of interesting. So here's the usual drunk and the masochistic drunk. So you can see, sure enough, the usual drunk, this fuchsia line, is progressing very slowly. And the masochistic drunk considerably faster. I looked at these, and after looking at those two, I tried to figure out whether there was some mathematical explanation of what was going on, and decided, well, it looked to me like the usual drunk was moving at about the square root of the number of steps. Not so odd to think about it if you go back to old Pythagoras here. And sure enough, when I plot, and I ran this simulation up to 100,000 steps.
Remember, because the square root of a squared plus b squared equals to c.
Of the number of steps, it's not identical, but it's pretty darn
close. Because you have those squares that are applied to the a and b coefficients.
Faster than the square root, but not much. But who knows?
But it's all nested under that square root, so it pretty truncates it pretty close right down.
The masochistic drunk seems to be moving at a rate
linear.
of num steps times 0.05.
Actually, no, it's 0.05 because it's
kind
half.
of a less intuitive answer than the square root.
Or not even half. It's like way
Why do you
less.
think it might be
5%.
doing
0.05.
Well, what we notice is that, and we'll look at this, maybe there's not much difference between what the masochistic drunk and the usual drunk do on the x-axis, east and west. In fact, there shouldn't be.
Yeah.
But there should be a difference from the y-axis.
Yeah, because
every time,
weight and bias towards the north.
1/4 of the time, the drunk is taking a step north.
It's a little bit more
1.1 units.
Than the
And 1/4 of the time is taking a step south
of negative 0.9
0.9 units. And so half the time, the steps are diverging by a small fraction. And if we think about it, 0.1 half the time.
Minus 0.9.
We divide it, we get 0.05.
0.05.
Okay? So
that's where that number comes from.
There's at least, we need to do some more analysis, but the data is pretty compelling here that it's a very good fit. Well, let's look at the ending location. So here you see a rather different kind of plot. Here, I'm showing that you can plot these things without connecting them by lines. So, and giving them different shapes. So what here I've said is that the masochistic drunk, we're going to plot using red triangles. And the usual drunk, I'm going to plot using black plus signs.
Rip Twitch game. Forgot about it.
And since I'm going to plot the location at the end of many walks, it doesn't make sense to draw lines connecting everything. Because all we're caring about here
is one final point.
The endpoints.
And they don't have any
So
relation
since I only
to
want the endpoints,
the inner steps, right? So we don't want to
plotting them a different way. So
Just a
for
scatter
example, I can write something like plot
dot scatter
x vals, y vals, and then if I do something like, let's see, dash B0, or just B0 in fact, what that says is plot blue circles. I could have written, in fact, I did write K plus, and that says black plus signs. And I don't actually remember what I did to get the triangles, but it's in the code. And so that's very
Blinkers, how's it
flexible
going,
what
my
you
guy?
do. And as you can see here, we get the insight I communicated earlier, that if you look at east and west, not much difference between this ball and that ball, right? They seem to be moving about the same spread, the same outliers. But this ball is displaced north. And not surprisingly, after 10,000 steps, you would not expect any of these points to be below 0, where you'd expect roughly half of these points to be below 0.
Yeah.
And indeed, that's about true. And we see here what's going on, that if we look at the mean absolute difference in x and y, we see that not a huge difference between the usual drunk and the masochistic drunk. There happens to be a distance, but a huge difference
in the y.
X and x. Comparing the two y values, there's a big difference.
Yeah.
As you see here. So what's the point of all this? It's not to
They're
learn
all
about
relatively in the
different
same
kinds of
X
drunks.
grouping, right?
It's to show how by
That Y grouping's
visualization
almost
we can get
500
insight
units
into our
greater.
data. That if I just printed spreadsheets showing you all of these endpoints, it would be hard to make sense of what
Hey,
was
Veer,
there.
how's it going?
So get
We're at MIT
accustomed to using
60002
plotting
right
to help
now.
you understand data.
Lecture 5.
All right.
Feels
Now
like
let's play a little
wormholes.
bit more with the simulation. We looked at different kinds of drunks. Let's look at different kinds of fields. So I want to look at a field with what we'll call a wormhole in it. For those of you of a certain generation, you will recognize the TARDIS. So the idea here is that the field
What do you
is
call
such
me?
that as you wander around it, everything is normal, but every once in a while you hit a place where you're magically transported to a different place. So it behaves very peculiarly.
So you have initialize with a number of
So
holes.
let's call this an odd
range,
field. Not odd numbers, but
100
odd
by
is
100 grid.
strange.
Right?
So it's going to be a subclass of field. We're going to have a parameter that tells us how many wormholes it has. default value of 1,000. And
Okay.
we'll see how we use X range and Y range shortly. So what are the first thing we do? Well, we'll call field underbar init to initialize the field in the usual way. And then we're going to create a dictionary of wormholes.
Okay.
So for W in the range number of wormholes, I'm going to choose a random X and a random Y.
Between the negative X
In X
range
range,
and a positive X
minus
range.
X range to plus X range, minus Y range to Y range. So this is going to be where the wormholes are located.
Should be X range
And then
plus
for
1.
each of those, I'm going to get a random location where you're, in some sense, teleported to if you enter the wormhole.
Or is random include the actual?
So here we're using random to get random integers. We've seen that before. And so the new location will be the location of the new X and the new Y. And we're going to update this dictionary
So
of
for every
wormholes
wormhole,
to
we're
say
going to get
that
an X
paired
and a
with the
Y
location
value,
X,
which is
Y
a random value between the X and Y
is
range.
new loc.
We're going to get new X and new Y, which is a random value between the X value and the Y range.
Now when we move the drunk,
And we assign
again, this is just changing,
new location,
we're
a
overriding move
location
drunk,
as
so
new
we're
X, new Y.
overriding one of the methods
And then
in
on
field.
the XY wormhole index
So
tuple,
field.moveDrunk
we're going to assign that new location.
will take a self and a
So
drunk.
we're just creating 1,000 random wormholes with a random
It's
location.
going to get the X value,
Okay.
the Y value, and if that is in the wormholes, it's going to move the drunk to the
So it's gonna-
location associated with that wormhole.
It's going to check then
So we
if
move a
that
drunk,
XY
And if the
tuple
drunk
is in
ends
the
up being in the
wormholes.
wormhole, he gets transported.
Then we're going to assign
we're
the drunk a
using
new location of the
field.moveDrunk.
wormhole location.
So notice that we're using the move drunk of the superclass,
We're just creating like a random
even though we're
mapping
overriding
that
it here.
if
Because we've
a drunk
overridden it
happens
here,
to hit
I
a
have to say
place
field dot to
on the
indicate I
field
want the one
that
from
also
the
correlates
superclass,
to
not
a
the
wormhole,
subclass. And then
then it
we're doing
transports you
something
to the random
peculiar
mapping
after the move.
value. Pretty simple.
So interestingly here, I've taken, I think, a usual drunk and plotted the usual drunk on a walk of 500 steps, one walk, and shown all the places the drunk visited. So we've seen 3 kinds of plots, one showing how far the drunk would get at different length walks, one showing all the places the drunk would end up with many walks of the same length, and here a single walk, all the places the drunk visits. And as you can see, the wormholes produce a profound effect, in this case, on where the drunks end up. And again, you have the code, you can run this yourself and simulate it and see what you go. And I think I've set random.seed to 0 in each of the simulations in the code, but you should have play with it, change it to just see that you'll actually get different results with different seeds.
Okay.
All right. Let me summarize here and say
Almost
the
done,
point
7 minutes.
of going through these random walks is not the simulations themselves,
How we
but
built them.
how we built them. That we started by
We don't care
defining
about
the
the
classes.
drunk. He wanted to, like I said
We
earlier,
then
the
built
point of
functions
understanding
corresponding
the simulation
to
itself.
one trial, multiple trials, and reported the results.
Of like as a whole, like what we're
And
doing.
then
Not
made a
the
set of
individual
incremental
simulations.
changes to the simulation so that we could investigate different questions. So we started with a simple simulation with just the usual drunk and the simple field. And we noticed it didn't work.
Hey, Polly Ron, how's it going, dude?
How did we know it?
Poor
Well,
drunk.
not because when we did the full simulation, we had great insight, right? I probably could have fooled half of you and convinced you that that was a reasonable answer. But as soon as we went and did the sanity check, where we knew the answer, we could know something was wrong. And then we went and we fixed it. And then we went and we elaborated it at a step of a time. I first got a more I shouldn't say sophisticated, a different kind of drunk. And then we went to a different kind of field.
Yeah.
Finally, we spent time showing how to use plots to get an insight. And in the remaining few minutes of the class, I want to go back and show you some of the plotting commands to show you how these plots were produced. Since I knew I was going to be producing a lot of different plots, I decided I would actually not spend time worrying about what kind of markers, those are the things like the triangles and the plus sign, or what colors for each one individually, but instead I'd set up a style iterator that would just return a bunch of different styles. So once and for all, I could define n styles, and then when I want to plot a new kind of drunk, I would just call the style iterator to get the next style. So this is a fairly common kind of paradigm to say that I just want to do this once and for all. I don't want to have to go through each time I do this. Get this window. Oh. So here it is.
So we have a style iterator of m dash, b dash dash,
that I'm going to iterate through. Style 1 is going to be an M, I guess
magenta.
That's maroon, with a line, a blue with a dashed line, and green with a line with a comma and a minus sign. So these are called the styles, and you can control the marker if you have a marker.
What?
You can control the line, you can control the color. Also, you can control the size. You can give the sizes of all these things. What you'll see is when you look at the code is I don't like the default styles things because when they show up on the screen, they're too small. So there's something called RC params. Those of you who are Unix hackers can maybe guess where that name came from. And I've just set a bunch of things, like my default line width will be 4 points. The size for the titles will be 20. You can put titles on the graphs. Various kinds of things. Again, once and for all, trying to set some of these parameters so they get used over and over again. Here, you'll see that I did things like you want to put titles on the slides. So on the graph, so here's the location at end of walk. Title is just a string.
Okay, this is just basically
you
showing
want to
us
label
like
your
matplotlib
here's
stuff.
not is that you don't. There's almost surely a way to make it do that. We'll move on, and in particular, we'll look at walks. Next lecture, we're going to move on. No more random walks. We'll look at simulating other things, and in particular, we'll look at the question of how believable is a simulation. See you Wednesday if the world has not come to an end.